For this question, we're going to be determining whether or not some of the compounds we have, if they are polar. So taking a look at water, our central atom is going to be the oxygen. We're going to have a total valence electron count of 8, so our molecule may look something like this. So because oxygen is more electronegative compared to the hydrogens, it's going to pull electron density away from the hydrogens, so it's going to make the oxygen partially negative, while the two hydrogens are going to be partially positive. So we do get an overall dipole moment of this, where the arrow is pointing up because the hydrogens are more partially positive and the oxygen is partially negative. So the head of the arrow is the more negative side. So yes, water is going to be polar. So let's take a look at another example, SF2. Our central atom is S because it's less electronegative, but then we also have a total valence electron count of 20, so we might draw a molecule looking like this. So because sulfur is less electronegative compared to the fluorines are going to pull electron density away from the sulfur. So you're going to have an overall an overall dipole moment with the arrow pointing down. So this molecule is polar. So taking a look at PCl3, our central atom is going to be the P. Our total valence electrons are going to equal to 26. And it's going to have a tetrahedral-like shape that is missing the axial bond. And so it kind of looks like a tent. So then in this case, we know that our phosphorus is less electronegative compared to our 3 chlorines. So our 3 chlorines are going to be partially negative while our phosphorus is going to be partially positive. So we also have an overall dipole moment pointing downwards, which does make this molecule polar. So moving on, let's take a look at Ci4. Our central atom is going to be the carbon, and it's going to be bonded to four iodines with a total valence electron count of 32. So here is our structure. We have a tetrahedral structure here. So because the chlorines are more electronegative compared to the carbon, it's going to be pulling electron densities away from the carbon. But it's pulling electron densities in 4 different directions in all equal magnitude. In this case, if you turn the molecule around in any direction, it's going to look the same. So there is a no net dipole moment, so this makes it a nonpolar molecule. So looking at SO3, our central atom is the S. We will have to draw a molecule like this. It's going to have a trigonal planar geometry in order to fulfill the oxygen octet rule. So taking a look at this, because sulfur is less electronegative compared to the oxygens, the arrows are going to be pointed towards the oxygens. Our oxygens are going to be more electronegative compared to our sulfurs. But again, similar to the Ci4, they're going to be pointed in 3 different directions, all in equal magnitude, so they're going to all cancel out. So we don't have an overall dipole moment, so this molecule is not polar. Finally, for SeO2, our central atom is the selenium, and we might draw our structure looking like this. So it is bent or V-shaped, and because the oxygens are more electronegative compared to the selenium, it's going to pull electron density away from the selenium, so our selenium is partially positive, and our oxygens are partially negative. So we're going to have an overall dipole moment pointing downwards, so this is going to be also a polar molecule.